Okay, we're going to do a simple set theory proof. Set A, we're going to take the union of that with this set B intersection C, and that's going to be equal to this A union B intersected with A union C. And so we're going to do it, I'll show it the proof using logic, and then after that we'll look at the pictures, the Venn diagrams, and see what that looks like. Okay, so what we're going to rely on here is the one that says, it says distributive law. It's the 1, 2, 3, fourth one down. P or Q and R is logically equivalent to P or Q and P or R, which is a law of propositional logic, easily verifiable using if you make your truth tables, and that's what we're going to use here. Okay, so for this set right here, for some member to be in this set, what we want to do is show that it has to be in this set, and then for some member for every member in this set, we want to show that it's in this set, and then for every member in this set, we want to show it's in this set. Okay, to do that, we're going to consider a member of this set, A union B C, and that means that X is in A or X is in B intersection C, which means I'll come down here, X is in A or X is in B and X is in C. Okay, so now we have this P or Q and R. So we're going to rewrite that using our distributive law. P or Q and R is P or Q and P or R. So we're going to rewrite this as, this is logically equivalent to X belongs to A or X belongs to B. This is our P, Q, R. So this is our P and our Q. Then we have the AND. Then we have a P again, which is X belongs to A. Then we have the OR. Then we have our R. X belongs to C. So that follows the distributive law. This one right here, P or Q and R is logically equivalent to P or Q and P or R. Okay, but what does this mean? What does this right here mean? It means X is in A or X is in B. That means X is in the union of A and B. And what does this mean? This means that X is in A or X is in C. It means X is in the union of A and C. So this is a set, and this is a set, and we have an and, X is in this, and X is in that, so that means X is in the intersection of those two. So X is in A union B and intersected with A union C. So we took a look at, up here, we started with if any element belongs to this set, then it belongs to this set, and vice versa, which is why we had this biconditional statement here. That's true, right? Each of these being the biconditional statement, we're looking at it both ways. So X is in this set implies that it's in this set. So any element of this set is in this set. And then the reverse is true. Any element of this set is in this set. And then we keep doing that all the way to the end. So the union of A and B intersected with the union of A and C is equivalent to A union B intersection C. All right, now let's take a look at what those Venn diagrams would look like. Okay, so here we're going to take A, and we're going to take the union of that with the intersection of B and C. So here's the intersection of B and C, and we're going to combine that with, we're going to make a union with A, and we get this shaded region in the Venn diagram. Okay, so that's the left side of the equation. On the right side of the equation, we have the union of A and B. So set A, set B, we're going to shade that in blue, the union of A and B, and then we're going to take that intersection of that with the union of A and C. So let's take a look at the union of A and C. Okay, now what we want to keep, we want the intersection. So what we're going to keep is anything where there's a blue and a red. So we want what's in common. So we're going to keep A, because everything's blue and red was shaded there. And then we're also going to keep this intersection of B and C right here. So these two sets of elements, these two expressions for the set of elements actually represent the same sets of elements.